Hopefully, we might be able to complete alkene today. But there are a lot of stuff that we must consider in order to complete alkene. So this morning, you're taking your time. I will share the slide with you, and we can quickly start the class. In the last class, we revised or we finished the alkanes, and we solved some past questions. But today, we also started alkane as well. We did some bit of introduction to alkane, and then we stop at isomerism in alkene. And so we said alkene can exhibit structural isomerism as well as geometric isomerism. I made mention that isomerism is of two types, and I said that we have structural isomerism and stereo isomerism. Under structural isomerism, I did not talk about it, and today I might be tempted to talk about it. But let me just give you a breakdown of that. Under structural isomerism, we have chain isomerism. Chain isomerism. Let me quickly write that one down for you. We have structural isomerism. Structural isomerism. Under that, we have chain isomerism. We have functional group isomerism. Functional group isomerism. And the third one is the position isomerism. Position isomerism. So the three types of structural isomerism we have. Of course, you know that structural isomerism is a type of isomerism where an organic molecule will have the same chemical formula but different structural formula. So the different structural formula can be in the form of chain or can be in the form of functional group differences or in terms of the position of the species, like chlorine in carbon 1 and also in carbon 2. That is different position. So that is about structural isomerism. So we have chain, functional, and position. And I'm going to give you, before I go, you don't know, I didn't plan to teach you, but let me quickly talk about it. Under chain isomerism is a type of isomerism whereby a molecule will have the same functional group, but they will have they'll have different position of the chain. Like I have a molecule here. We have propane. This is propane. Okay, butane. Then we can have this molecule this way. This is an example of chain isomerism. We have here straight chain. We have split chain. We have branch chain. So structural isomerism is a type of isomerism whereby a molecule have the same structural formula, the same chemical formula, but different structural arrangement, whereby one is straight chain, the other one has branches. So we have, this is an example of a chain isomerism, because there's a branch here where we have 2-methyl butane. So 2-methyl is a chain isomer of butane, the normal butane, 2-methyl butane, because structural isomerism is only found, is mostly common with alkane, like that. Another example of structural of chain isomerism, we can have something like 1, 2, 3, 4, then 5. This. And then we have 1, 2, 3, 4, 5. Okay. Now, this molecule, they all have the same number of carbon. If you look at this number 1, 2, 3, 4, 5, 6, 7, 8 for A, and B 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Then we can have 1 to 8 here, looking at 8. So they all have the same chemical formula, but different branches. A is 2,2,3 trimethyl pentane. That's A. 2,2,3 trimethyl pentane. 2,2,3 trimethyl pentane. But B is carbon 1. B is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6 on carbon. So that is not the correct numbering. 1, 2, 3. So B is 3,3-dimethylhexane. 3,3-dimethylhexane. They are both structural isomers and chain isomers of each other. They are chain isomers because they have different branches. So we have chain isomerism, whereby a molecule have the same chemical formula but different structural arrangement. One having branches, the other one may not have branches, or we have different branches, or simply straight chain. We call that one chain isomerism. So that's about chain isomerism. Let's look at functional group isomerism. Functional group isomerism. In functional group isomerism, a molecule will have the same chemical formula, but different functional group. The same chemical formula, but different functional group. This kind of isomerism is common with alcohol, and ethers. Number 2, between carboxylic acid, and esters. Between carboxylic acid and esters. And number 3, you will see that between alkenes and alkane. The alkane must be cyclic. So under functional group isomerism, a molecule will have the same chemical formula, but
excuse me, sir.
different functional group. Any question?
Yes, I have a question, please. Did you say that only the alkane is cyclic, or both of them?
Yes, just cyclic alkene and alkene.
Sorry?
The alkene must be cyclic alkene.
So I
There is,
didn't get you. I
I
didn't
mean,
get you.
alkene
Your word.
and cyclic alkene that can form a functional group isomerism. Not the
Okay,
alkene.
alkene and cyclic alkane.
Yes, yes.
Okay.
All right. So let's look at the first one, the alcohol. The first one, alcohol and ethers. Ethers are compound having oxygen between two alkyl groups. Ethers are compound having oxygen atom between two alkyl groups. For example, if an alkyl group is ROR, so there's an oxygen here. So we have, if the first R is CH3, goes to O, goes to C3. We call this one dimethyl ether. Dimethyl ether. So that's just a simple explanation for ethers. They are molecules containing oxygen atom between two R group. The R group may be the same, or the R group may be different. If the R group is different, for example, the H3-O C2H5, like this. The longest R group will be used to name the molecule. So we have here ethyl, ethyl plus oxygen. That will be ethoxy. Ethyl plus oxygen, ethoxy. Then this is from methane, ethoxy, methane, ethoxy, methane. All right. Ethoxy, methane. It's like methane is the parent compound. So hydrogen was removed. So we have ethoxy, methane, ethoxy, methane. When that is a IUPAC name or IUPAC name. But when you come to like giving the normal common name like dimethyl ether, you use alphabetical. Methyl for the other one is ethyl. So ethyl, methyl ether, E come before M. That will be ethyl, methyl ether. That is for the common name. But the IUPAC name is ethoxy methane. From here, ethoxy, the methane. Okay. Now that we have idea of what ether looks like, let's look at the isomers. That is the functional group isomerism between alcohol and ethers. Now, let's take the first one, alcohol and ether. Let's look at ethanol, C2H5OH. In terms of structure, we can have this. Okay, that is ethanol. The isomer, which is an ether, the oxygen atom is coming to the center carbon, the in between the two carbon atom. So you're going to have CO to C, and then you have this. Luckily for your syllabus, both common name and IUPAC name are allowed. So this is dimethyl ether or methoxy methane. So common name and IUPAC. IUPAC. So that is that. This is ether homologous series, and this is a alcohol homologous series. So we call that one functional group isomerism, where a molecule will have the same formula but different functional group. The functional group here is alcohol, and the functional group here is ether functional group. So ether and alcohol, they exhibit functional group isomerism. And if you have more than 2 carbon atoms, you can vary the position of the oxygen atom. For example, if I have 4 carbon atom, and I have my OH here, that would be butanol. I can try to put the O on carbon 1 in this form. So I have this. In this case, we're going to have methoxy, we're going to have propoxymethane. Propoxymethane. And a functional group isomer for butan-1-or butanol or C4H9OH. This molecule, C4H9OH. So we have butan-1-or. Any of those butan-1 can be butan-2-or butan-1-or butan-3 or anywhere it is. One is an alcohol. Propoxymethane.
So I have a
Also
question.
an isomer. Yes.
For ethers, how can you identify, let's say like the propoxymethane, how did you not know it was like you took the functional group to the other side, like you used the CO instead of the CCCO? Like how could you identify that?
You mean if I have 3 carbon atoms before naming it?
Oh no, like what if you had what if it was methoxy propane? Like, how would you know it's propoxymethane, not methoxy
Okay,
propane?
propoxy. If how would if it's propoxy?
How
It
would
does
you know it's that, not the
it
other
does not
way?
matter the arrangement. What decide the name is the longest carbon chain of the ether molecule. The longest carbon chain. For example, assuming it is like this. Is this what you're saying?
Yes,
Is it like this?
yes.
Okay. What matters most is the longest carbon chain before the oxygen atom. So it does not matter the side where it is. This is still going to be propoxymethane because the longest carbon chain take more uh, takes more power than the shortest carbon chain. And we have difficult one. What of the one that has a side chain? That one is still there. If the O is on carbon 2, like this one, have O here, then have CH3, have this. So we have the difficult one. This one is on carbon 2. This one is on carbon 1. The O, the this one is on carbon 1. This one on carbon 1. But this one, the OCH3 is on carbon 2. You see that? So what matters most is the longest carbon chain carrying the oxygen atom. So in this one now, in this one, it will be the longest carbon chain, carbon 1, carbon 2, carbon 3. Carbon 2, we have OCH3 attached to it. So 2, all right? So here now, here will be 2-methoxypropane. That will be the name. On carbon 2, we have methoxy. So it will be 2-methoxypropane. 2-methoxypropane. true methoxypropane is also an isomer of C4H9OH. All right.
So
While
sorry. I have a question. The name at on the left,
yes,
propoxymethane.
this one,
Yes, propoxymethane.
yes,
Which is it for again? Which structure is it for again? That you
so
drew?
it should be what?
I know, like the propoxymethane. Which one is it out of like the structures that you drew?
Well, I think what we are saying, this one, um, the only adjustment that can be made is to put that is on carbon one. So we can just say here, um, yeah, one propoxy methane. One um I was talking about the carbon atom proposing methane. So here one propoxy methane, one propoxy methane.
Okay,
So
so the
yeah,
longest carbon chain will carry the functional group.
I'm coming. Here we have two methoxy propane. We have yes, 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 yes. Let me make one correction. Yeah, let me make one correction. For this one, for this one, and this one, they are the same. Okay. And I said the name will be propoxy methane. Propoxy methane. The actual thing that should be there, the longest carbon chain is the one that loses the hydrogen atom for the other one to join. Okay. So it will carry the main name, the real name. So here this was supposed to be propane. So here will be one methoxy propane. Sorry about that. That's a mistake here. That's a mistake here. So here should be
Yes.
one. This one. This is carbon one. Let me carbon one. Okay. So carbon. This is carbon one, carbon two, carbon three. So here should be one. How you back name now? One methoxy propane. Kindly correct it, please. One methoxy propane. That is that. One methoxy propane.
How is it one?
One, because this, the longest carbon chain is one, two, three. Carbon one, carbon two, carbon three. On carbon one, on carbon one, you have methoxy attached to it. Methoxy
Oh,
is,
okay, okay, okay,
yes,
okay.
so one methoxy propane. The same thing with this one, carbon one. This is carbon one, carbon two, carbon three. You can't say carbon one is here. No, you start counting from the functional group. The O there is the functional group. The hyphen O hyphen is the functional group there. So carbon one is this one, carbon two, carbon three. So one methoxy propane is the correct answer for this one. While this one, the longest carbon chain is one, two, three. So on carbon two, you have the OCH3 attached to the methoxy attached to it. So this one is two methoxy propane, two methoxy propane. So kindly take that correction and adjust it to the previous slide that I explained. So let's take more example on that one again. Let's take more example to cement it. So you can have under this naming, let's look at another O C this. this, and we have another one. Okay. All right. So look at this. Let's call it A and B. Let's look at A. The longest carbon chain has 3 carbon atoms, and the numbering should start from where the functional group is. So we have carbon 1, carbon 2, carbon 3. So on carbon 1, we have ethoxy. So here will be ethoxy propane, or methyl propyl ether, the old name. This is ethyl. This is ethyl, and this is propyl. So ethyl propyl ether, for the old name. The B now, B, they have both, we have a carbon 1, carbon 2, carbon 3, longest carbon chain. So carbon 1, again, you have the ethoxy. So ethoxy propane, they are the same molecule. It does not matter where the longest carbon chain lies, about the same name for the two of them, the same name. But when you have it this way, if you have it this way, so when you see this one, it's not a big deal in your exam. When you were asked to name it for your AS chemistry, you already have an idea of naming of ether. Okay. This one, you already know that the longest carbon chain is 1, 2, 3. So on carbon 2, you have ethoxy. We have methoxy rather, and so therefore 2 methoxy propane, 2 methoxy propane. I think it's okay like that. Are you
Yes,
still
sir.
there? I said, I hope that is okay for the naming.
Oh, yes, sir.
Okay, so you will give me the name of this one to be sure that you understand. So, okay, so just name this one, then you can continue. Yes. I said you should name this compound.
Okay. Um, two, um, yeah, two ethoxy, propane.
Okay, 2-ethoxy propane. Then they ask you, give one isomer of that is an alcohol. One isomer of it that is an alcohol. Then just know that alcohol and ether, they are isomer. Just count 1, 2, 3, 5 carbon atoms. So anyone that comes to your brain, 5 carbon atom, 1, 2, 3, 4, 5. Then you can just draw isomer OH. And so you are done for the simplest one, the straight chain, and you are done. So if you're also given alcohol and give one isomer that is the same formula, but it's an ether, you can you can do anything as long as they have the same chemical formula. So the purpose of this slide is to let you know that alcohol and ether, they are functional group isomers. That is that. We go to carboxylic acid and ester. I hope you know what we call an ester.
Yes, I have an idea.
Okay. An ester is a molecule with the general formula of CN, H2N, COO, CN, H2N. Plus one, plus one. But let me just tell you that an ester is a compound form when an organic acid like ethanoic acid react with an alcohol like C2H5OH in the presence of concentrated sulfuric acid to form an ester. The ester is formed when the OH from the acid is removed and is joined with H from the alcohol to form water. In writing the formula of the ester, you write the remaining part of the acid first as CH3, CO, then you write the remaining part of the alcohol, beginning from the oxygen atom. So O, then C2H5. And then water was removed. So this is an ester. So an ester is a compound produced when an organic acid and alcohol react reversibly in the presence of concentrated sulfuric acid to form a sweet-smelling compound called ester. It's a reversible reaction. It must be reversible, and it also requires heat as well. Without heat, there is no reaction. You have to heat the alcohol with the carboxylic acid, strong heating with sulfuric acid to give you an ester, and water is also a byproduct. So this ester and carboxylic acid are what? Functional group isomers. Now, there are 4 carbon atoms there. Okay, this is your first R, and this is second R. So we have R1, we have R2, but then we have the functional group. So we have the hyphen C double bond O, like this. That's the functional group in ester. This one is different from the one in carboxylic acid. The one in carboxylic acid is hyphen C double bond O, OH. This is the functional group in carboxylic acid, hyphen COOH. But the one of ester is hyphen COOR. So they are different. But when it comes to isomerism, both ester and carboxylic acid are functional group isomers. So let's take an example, because now you now know what we call an ester and then what we call the carboxylic acid. But before I do that, let me quickly draw the structure of this ester for you so that you can look through it and be able to conceptualize other structure that we'll be drawing later. So the structure of that ester, you start from the COO here, the carbon here, the first oxygen atom is double bond like this. The second one is single bond. Then you can now add your C to C in this manner. So you have your, then the other one, we have 2 carbon as well. I've taken one, remaining one. So add it like this. So this is a 2D diagram of an ester. 2D diagram, not 3D, 2D, because this angle is 180. As this angle is 120. But the way it is now is 90. 90 because it's 2D. So when we get to ester, we'll talk about the angle, but now we're only just drawing the diagram on 2D. So this angle is looking like 90, but it's not 90, it's actually 120 because it's trigonal pyramidal. It's like this. So double bond is like single. This is 120. So then it's CO like this. So it is 120, but that is not the bone of contention for this class. So now to name this molecule has to be named. You name this one. This one is not ethoxy like we used in ether. No, the O does not join the ethyl. The O remains with the COO as it's a functional group. So the O is not removed from the other O. So you only name the ethyl, the R group alone. This R group alone is named alone, separately. So you start from the R group, this R group, from this R group. So the R group there, this R group is ethyl, ethyl. So we have ethyl. Then you name this one together, C3COO. C3COO is ethanoic acid. By the time it forms an ester, it becomes ethanoate. So the suffix, what ends the name of an ester is OATE. OATE. Therefore, ethanoic will end with ethanoate. So carbon 1, carbon 2. So ethyl ethanoate. Ethyl ethanoate. Ethyl ethanoate. Okay, ethyl ethanoate. If you increase the carbon, this one, and you add another carbon here, it becomes ethyl propanoate. Ethyl propanoate. If you remove this carbon atom and put it back as H, and then you remove this one and then bring in a CH3, it becomes propyl ethanoate. Propyl ethanoate. If you remove all of this one and you put H there, it becomes propyl carbon 1 methanoate. This is methanoate. Methanoate. Why? Because we have methanoic acid. So methanoic acid can react with propanol to form propyl methanoate, like that. So that is about that. So let's look at example of of carboxylic acid. This is carboxylic acid. 1, 2, 3, OOH. We have C double bond O. We have C double bond O. C double bond O, OH. Okay, so we have this is ethanoic acid. How can we form an ester from this one? Let's take the first ester. Let's have it this way. Let's look at it this way. H, C double bond O, then CH3. If you look at this molecule, you will see that the chemical formula is C2, 1, 2, 3, 4, 1, 2, 3, 4, 5, H5, then O2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1. Okay, so we are going to have here 1, 2, 3, 4, C2, H4, O2, C2, H4, O2. So this one is an ester. It's an ester, while this one is a carboxylic acid. They both have the same formula, but different functional group. One being an ester, one being carboxylic acid. So functional group isomerism is a type of structural isomerism whereby a molecule will have the same formula but different functional group, like that. So take any carboxylic acid, you can form an ester from it. Any carboxylic acid, you can form an ester from it. That is the simplest example of that. Imagine this girl was not in the classroom, and I got to teach in the room. Hello, are you back now?
Yes, the internet went off and I had to do something with it. That's why I wasn't in class.
Okay. I did not
Yeah.
even, I didn't know. It was when
Oh,
you were,
sorry,
it was,
sorry, sir.
no problem. No problem. Okay, so let's continue. So I was explaining, did you get the explanation for um the isomer of carboxylic acid and ester?
The only thing I did what we stopped on was when you said that the ester ends in OH and you explaining that
Okay.
the OH comes from the carboxylic acid. So
Yeah,
yeah.
yeah, yeah. So let me re-explain it then. Let me re-explain it because I was talking when you were not. I didn't know that you left. Okay. Um, let me. Okay. So let me re-explain it. So um, this I put something here as um, okay. I was talking about carboxylic acid, and I said this diagram of this one is ethanoic acid, ethanoic acid, ethanoic acid. Now, ethanoic acid, we can bring in an ester from ethanoic acid, and they will have the same formula. So, in doing that, to bring in an ester, what I did was that I counted the carbon atom. There are 2 carbon atoms there and 4 hydrogen atoms. To form an ester, I know that methanoic acid can form an ester. So methanoic acid will have 1 carbon. So double bond like this, H. Then second O, then the last carbon atom this way. This is an ester, methyl methanoid. Methyl, this one. Methyl, then this is the methanoid, the acid part of it. Methanoid. Methanoid. So this compound, this ester, has the same formula as C2H4O2. and the same thing, both of them have the same formula, but different functional group. One is an ester, the functional group, and one is carboxylic acid. So carboxylic acid and ester, we should know that one it should sound permanently in your brain because of your AS chemistry when they will be bringing out isomerism, and it will not be funny at all that when they be asking a question in this area. Let's take one more example. Let's take one more example of that. Let's look at propanoic acid. Propanoic acid will be CH3, CH2, COOH. So we have 6 carbon atoms. So we have C3, H6O2. That is the formula. And let's draw the structure. The first carbon, second carbon, then the third carbon carrying C double bond OH. So we have a display formula. Now we are using display formula. So that is a propanoic acid. That is a propanoic acid. And the other one, the ester of that, let's look at this carbon one, this one. So in that carbon one, I'm writing everything out like this as HCH3. Then I will bring in the ester like this. So I have 2 more carbon remaining, and that one will be, no, 1 more carbon. We have used 2 carbon, so 1 more carbon remaining like this. You will see that there are 6 hydrogen atoms and 2 oxygen carbon, 2 oxygen atoms. So this is an ester. How do we name this ester? You start from the side having the alkyl group. So methyl, we have 2 carbon atoms. Ethanoate. So methyl ethanoate and propanoic acid, they are isomers of each other because they have the same chemical formula of C3H6O2, but different functional group. So we call them functional group isomers. Functional group isomer. And you can draw another ester again from this one. If you make carbon 1 the functional group, like here, C double bond O goes to O, then CH2, then CH3. So we have ethyl methanoate. Ethyl methanoate is also an isomer of propanoic acid, like that. So draw one isomer of this molecule, that is carboxylic acid, and 2 isomer, that is an ester. You can just juxtapose. So you can have this one, you can have this one, or you can have it the other way around. So it is a lot easy. So 1 propanoic acid, 2 esters, like that. Okay, that's about carboxylic acid and ester. I hope it is clear.
Yes, I just want to write something down quickly, please.
All right.
Please, I just want to take this down. Sorry.
When you are done, so let me know.
Okay, I'm done.
Okay. Okay. All right. So now the other one I said alkane and cycloalkane are isomers of each other. Alkane and cycloalkane. Let's look at the alkane. Let's look at an alkane. Can you give me an example of an alkane?
Did you say alkene or alkane?
Alkane. Example.
Um,
Yes.
propene.
The propane. All right. Propane. And that will be CH2. I'm writing it the way this is how students write it to in the exam. This is how students do write their own propane, which is wrong. And you ask me what is wrong with this one. This is how they write it in the exam. But they will give you the actual way of writing it is like this. The actual way to write it is like this. Because the bond angle there is 180. So we have this one. We have CH3. We have H, we have H. That is propane, standard propane. But this is 2D and this is 3D. Okay, that is just no problem. That is just that. Now we have propane. Propane. So let's look at the cycloalkane, three carbon atom, uh, carbon 1, carbon 2, carbon 3. Cycloalkane. H, 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 H. So we have C3H6. If you also look at this one, you look at the diagram, we have carbon, where the first hydrogen, second hydrogen, third hydrogen, plus 3C. So it's also C3H6. So you will see that propene and cyclohexane, they are friend of each other. This is a cyclo, cyclopropane, 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 and this is your normal propene. So they are isomer. You will see that double bond here, the double bond here is a functional group here, but the single bond here is a functional group. So they are also functional group isomer. So this one is also a soft spot in your organic chemistry under isomerism. They will tell you draw all the isomers of butane, all the isomers of butane. Draw all the isomers.
Sorry, before I forget, sir, next week, is it possible for us to look at paper 3 and paper 5?
Paper 3 and 5.
Yes.
Okay. Is
Just like have an overview, just to get like the hang of it before I start in school.
okay.
Especially paper 5. 'Cause I know we did some of paper 3 like earlier last year. So I just want to like start with paper 5 and like
Okay.
yeah.
Not then I think they don't during those days when we started this class, I did something on paper 3 for you under mold.
Yes, yes, I remember that. Yeah.
So we will talk paper 3 again, and then I will bring in more element of paper 5. And then also paper 5 has no syllabus than the whole syllabus. Any question can come out paper 5. That is in the syllabus. So there is no any. So all or any area in the syllabus is paper 5, as long as there's practical in it. So no problem. Is it going to be on the same class or another class?
Sir, what did you say?
Will it be on the same Saturday or another class for that?
The same Saturday if possible.
Okay, the same Saturday. So, okay, let's continue. So we are talking about all the isomer of butene, or butene, or all the isomer of C4H8, of C4H8. This one, of course, you know, in this question, C4H8. Let's look at it. We are going to have number one. We are going to have structural isomers of butane. Number two, I'm going to have cis-trans isomer. And number three, we're going to have what now? Functional group isomer. Functional group
What
isomer.
about what about position isomer?
What about what?
Position isomerism.
Position isomerism, that will be structural, under structural. So
Okay.
that then we're going to have the first carbon double bond like this. CH, CH2, CH3. That is your put one in, put one in. Then we're going to have CH2 double bond. We're going to have then CH double bond, CH, and CH3. This one can either be cis or trans. Trans both two in. Then you're going to have CH3, C into CH3, then double bond CH2 is another structural isomerism. Now let's make it clearer because I'm using structural formula now. Let's draw this one first. So we have CH3, then C carrying its side chain like this. Then also having a double bond, then CH2, H, 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 H. So that is, can you name that? Can you name it for me, this one? That'd be what?
Okay, that would be um two ethyl two methyl propene.
Okay. Is also a structural isomer as this one. So that would be, let's draw that one. The first one is very easy to do. Have C double bond to C to C. So we have students struggle with this structure because they won't know that they are supposed to bring in that onto carbon 2. They won't know. So this is your boot one in. So the two of them, 1 and 2, are structural isomers. And we call them position. It's not position now. It's not position at all. It's not position. They are both structural isomers. One is on carbon 1. That one is still on carbon 1 as well. But this is it's a chain isomers, we call it, because this is straight. This one is straight chain, and this is a branch. So they are branch isomers. But this one and this one, they are position isomers. So one of those years, they were asked to draw and a molecule with C4H8 that has that are both structural isomers of each other. So both 1 in and both 2 in are structural isomers or position isomers, because carbon 1 we have double bond, carbon 2 you have double bond. So for both 2 in, like this, both 2 in and both 1 in, they are position isomers because of the double bond being on carbon 1 and carbon 2. That is that. So draw a molecule having C4H8 that are isomers of each other in terms of position. So both 1 in, both 2 in, they are position isomers. But if you look at this one, and this one, they are different. They are not position at all. They are chain isomers of each other. Chain isomer, because one is straight chain, the other one is branch. Okay. Then if you look at this one, so we are done with position isomers for both 2 in for C4H8 and branch isomers, branch chain isomer. Now let's look at CIS-TRANS isomer for this guy. CIS-TRANS isomer, that's both 2 in. For both 2 in, both C4H8, both 2 in, the focus is on the double bond, both 2 in. So we have H, then we have H, then CH3, then CH3. So carbon 1, carbon 1, carbon 2, 3, 4. So that is both 2 in, but it is now cis, then hyphen, both 2 in, because there are two C3, C3 are on the same side of the double bond. But if they are across, each other, CH3 and then CH3 in this form, it becomes trans hyphen both 2 in. That is about that. Okay. So in C4H8, we are saying structural isomers. We are saying cis and trans isomers. And we are also saying functional group isomers and the rest. We can also look at this one. Is the same C4H8, the same C4H8. That's what cyclobutane is, a functional group isomerism with any of them. Because the other ones have double bond, is having a single bond. So cyclobutane is a functional group isomerism to cis-trans both 2 in or trans both 2 in or both 1 in or both 2 in or 2-methyl propene, anyone. So that's about that. So alkanes and cycloalkane are what now? Isomers of each other, especially functional group isomerism. We have spoken enough about structural isomerism. There is this molecule called this molecule. You will tell me the molecule because you should know it like this: H, then R, then this R. Can you remind me the name of this molecule?
The first one is ester.
No, alkanol. Alkanol.
Oh, oh,
Yes. So this is alkanol and alkanal. Alkanal. Alkanal is alkanone. We call them ketone, while alkanal they call them aldehyde. Aldehyde. They are also they also have they are also functional group isomers of each other. Functional group isomers of each other. For example, you will see that they both have C. This one has RCHO. Okay, we can start now. All right.
yes.
Okay. As I was talking before, that as I was talking before that aldehyde and ketone, and I said aldehyde are called alkanal, that's iopacname, and ketone we call them alkanone, also iopacname, and they can form a functional group isomerism because they have different functional group. So we look at that right now, then you can continue the slide. Okay. So looking at that, okay, let's look at okay. Okay, looking at that, under that structural, under that the other one, they both have different formula, especially the two of them. Let's just look at the formula, and then we can continue. Okay. For we have one of them has Cn H2n plus 1 CHO, that's the alkana. So if n is 1, if n is 1, n equals to 1, I'm going to have CH3 CHO. We call this one ethanol. 2 carbon atom, ethanol. So Al, instead of saying ethanol, you say ethanol. So OL goes away, then Al will replace it. If you have CH3, CH2, then CHO, propanol. So instead of saying propanol, to be propanol, they are never alcohol. They are never, this is alcohol. This is propanol. And this is how to draw the structure. The O is double bond O, then H. So propanol. So don't be deceived by thinking that the HO is OH. No, the HO is never OH. It is intentionally written as CHO. So this is propanal. The other one, ethanol, is like this: C to C, double bond, H. The 1, 2, 3. Ethanol. Then we don't have, this one does not exist. This one does not exist. Methanol. I don't think it is not stable per se. Methanol. When N is 0, when N is 0, methanol, CHO. It's not too stable, but you can see that methanol, ethanol, propanol. So it is CHO hyphen CHO. That's the formula. While the structure will be hyphen C double bond O, then H. That is methanol, ethanol, propanol. Now let's bring out the isomerism now. Let's look at the other one, the second group, which is a ketone. For the ketone, their own formula will be CnH2n, then that will be CnH2n plus CO, CnH2n plus 1 CO. Now, to make them isomers of each other, to make them isomers of each other, let's look at it this way. Let's look at propanol. Propanol, we have C to C, double bond. Then we have CH3. We have CH3. You know that I didn't plan this one this morning. What I planned for you was alkene. So we have, this is propanol, propanol. So let's look at propanol. The same formula. This is a 3,3. That will be C3H6O. Then if you bring in out propanol, the double bond O, H. 1, 2, 3, 4, 5. So we have the same, these 3 carbons, this hydrogen 1 O. This is propanol. Propanol. So they have different functional groups. They have, one has CHO, CHO, one have hyphen C double bond O, like this. R. This is a functional group, and that functional group. So they have different functional groups. So they are isomers of each other. In fact, functional group isomers. So I have explained position isomerism. I have explained functional group isomerism and chain isomerism in detail beyond what your teacher will have time to teach you in class, because he does not have time. What I've just done for you now is to bring in different topics together to explain structural isomerism for you. But your teacher will only teach them when it gets to when it gets to this one, ketone. I mean, when you get to this formula, they call this one name. I've forgotten that name now. They will also teach you alkene generally, and if you want to teach you that cycloalkene and those about, this is different from your normal classes. So it may not teach you this way, but this is part of what you gain when you do extra classes sometimes. So now I'm going back to my alkene. And the last class I was talking about the double bond in alkane is restricted. The double bond in alkane is restricted. It does not rotate. But there is no time to explain that. But if I may quickly explain that if it's, this double bond cannot rotate, so it is locked up, or simply using the word restricted rotation. Rotation only occurs when between only occur between this place. So this hydrogen can come here and this one can come here. So it can either go up or go down, go up or go down. That's all. But the two carbon atoms cannot be exchanged. Therefore, this molecule cannot form this one. It is not possible. It cannot. This one cannot form this one, because in this one you will see hydrogen here, but now it is not hydrogen here and here. No, because the carbon cannot move. What can only change is this one can come up or come down. That's all. Okay. Now, what do I mean by the term that it can rotate? Alkanes can rotate. They have unrestricted rotation. For example, if I have a molecule like this molecule, then I have chlorine here, I have chlorine here, and the other molecule are hydrogen, 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 hydrogen. This one can become this one, 1, 2, 3. Then I can move in the chlorine, I can bring it here, chlorine, I can bring it here, chlorine, and I will make the remaining one hydrogen. Because alkanes have unrestricted movement. Or I can bring it down here, I can put one here, sorry, I can put chlorine here, I can put chlorine here. Like this. So even though I've changed their position, but there is unrestricted movement. It can be anywhere, unlike alkene. Alkenes cannot move like this one. Besides the meaning of the double bond is locked, it prevents free rotation. Okay, that's about that one. Okay. Okay. So moving on to the next slide. And last week also we said that this one can form CIS-TRANS. So like this now, across both molecules are the same on both sides. Okay. So this is cis isomerism, and from that cis, we can have this one can come down. If it come down, then we can have we can have um, we can have H on top, then Cl down, double bond, and then you can see how your Cl up and H. So we have trans. So here we have cis and trans. It's correct. But when this one and they are the same, is wrong. It's wrong. They are the same on both sides, like this, on the same side alone, is also wrong. When all the four atoms are different, then you can have the same, you can have cis-trans isomerism. So there are two scenarios from that diagram, from the four diagram, that can give you cis and trans isomerism. So you must look at the group. Are they the same on the same side? No isomerism. They are the same on both sides, no isomerism. The four groups are different. There is isomerism. This one I explained last week. Okay, so I won't waste time. And like I said, that look at this guy. This one cannot form this one because of there is no free rotation. Then there is an element here. We are seeing Z and E. I will not waste too much time on it. The Z here is from a German word called Zu, Zusammen. Zusammen is a German word which means the group being on the same side. So Z isomer is the same as cis isomer. So the Z is from Zusammen, German word, from some guys. There are three guys that form that. But when we get there, we see the name there. They are very difficult name to pronounce, but when we get there, but so Z is Zusammen. Then we have E. It's also another German word from the word Ent. N Tijegen. That is it, Tijegen. So E is the same as the trans isomer. I will talk more about it when you have the same group across the double bond, the same group across double bond, you have trans or E isomer. So E isomer is trans, Z isomer is cis isomer. So the same group. What is the meaning of Zusammen? And so, like I said, when the group are on the same side, Zusammen, when the group are on the opposite, on the across the double bond is Tijegen, that's E isomer. Okay. Move on from there. Then we go on to the rotation of the double bond. You can see the double bond rotating two carbon atom, So there's chlorine on carbon 1, chlorine on carbon 2. So the chlorine on carbon 2 is not here. It's still carbon 2. It is also, it's still here, it's still carbon 2. So this molecule, they have the same name. This is 1,2-dichloroethane. 1,2-dichloroethane, 1,2-dichloroethane. Even though the chlorine atom appears to be like it's moving, it has free rotation, but it's still on carbon 2, it has not changed. So drawing the what's it called now, the skeletal formula of it. If you try to draw the skeletal formula, this one will like this one is like this. This is chlorine for this one. Then this one, number 2, is like this. So chlorine, and same thing. This one, number 3, like this, same thing. Chlorine. Or okay, that number, the second one, let me draw properly. The second one is like it's like this. Okay, so that has not changed. It has not changed. So there is the same thing is 1,2-dichloroethane for all of them. Okay, so that is rotation inside. You can see that one rotating. So okay, all right. So moving on to the next slide. Okay, the rotation permitted in alkane is only this one. Is only the one you are seeing now. This one. That is what you are seeing. See that you can only flip up and down, flip up and down. Therefore, this one cannot form this one. The same atom on the same side, it can't change and form this one. So cis cannot form trans because double bonds are already locked up in space. So the only thing possible is for the lower one to go up and the upper one to go down. That's all. That's only what is possible from this slide. And then move on. So to further explain the EZ isomerism, or E is your cis and Z is your cis and E is your trans. To further explain that, you will look at, let's look at this, what we have here. This is CH3, that's 15. Chlorine, that is about 71. No, sorry. Chlorine is what? 35. 5. Hydrogen is 1, 1. So this is a smaller molecular mass, higher molecular mass on the same size. When you have higher molecular mass on the same size, we call that one cis isomer, higher molecular mass on the same side. Then higher molecular mass across, chlorine is at 5, 15. This is 1, 1. Higher molecular mass across, that will be trans on the other one. The same thing, this is 15, 15, 1, 1. Higher molecular mass on the same size, you have cis, higher molecular mass across, 15, 15, 1, 1. Higher molecular mass across, you have trans, like that. So it can be in the form of higher molecular mass. So the EZ isomerism deals with higher molecular mass across or on the same size. Talking about EZ isomerism, higher molecular mass across or on the same side. Okay. Okay. I was talking about EZ the other time, the Zuzamen and Entijegen. Z for Zuzamen, E for Entijegen. And you can see higher priority. Higher priority means higher molecular mass. We have higher priority. Higher molecular mass, we have higher priority. Lower molecular mass, we have lower priority. So when higher molecular mass are on the same side, you have cis, and when you have higher molecular mass across, you have what trans, or which your E and Z. E is higher molecular mass across. Z is higher molecular mass on the same side. Higher molecular mass has to do with higher priority. So you can, if you come here, you will see that C2H5 is higher than CH3, and CH3 is higher than H. So the more the molecular mass, the higher the priority to identify whether it is E or Z isomer. Also, iodine has higher molecular mass compared to bromine, chlorine, fluorine, and hydrogen. So the higher the molecular mass, the higher the priority. So when you look at molecules like that, you can know that it's E or Z or EZ isomer, you know which one. While E is your trans and Z is your cis. It's confusing, but with time, you will certainly get it. And then we move on to the determine the higher molecular mass or lower molecular mass. There, like I said, the owner of that EZ, they are German guys whose name are called Kahn, Ingold, and Prelog. CIP, Kahn, Oliver Kahn. That is a footballer in those days, a keeper. So Kahn, Ingold, and Prelog, CIP. They are the founder or the owner of that of this EZ isomerism. So as you can see here, this one is higher molecular mass, higher molecular mass on the same side, and that will be cis isomer or Z isomer. Higher, so this is ethyl. Ethyl is 29, methyl is 15. This is 15 and 1. So higher molecular mass on the same side, we have higher priority. Higher molecular mass, we have higher priority. So we have, they are both on the same side, and that will give you your Z isomer, which is equal to cis isomer. They will hardly ask you to to do EZ isomerism. You are only to know it, but they will likely not ask you. Okay, so there is no big deal when it comes to that one. Just to know it, but I have not seen this question before. Okay, so if you look at this, also the same thing here. Here you will see that this is 2915. That will be your cis and trans. Sorry, that will be cis isomer. And you can say, if you want to name it, you can name it. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So that is pentene. Pentene showing EZ isomerism and locally showing the cis isomer or the Z isomer. Okay. Let's look at this one. Okay, it's still the same thing. Then let's look at here. Why the E here? Why the E is because higher priority across 2915 across. That's E. And E is your trans. Then we have higher priority on the same side, 1529. Z. Z is your cis. And here we have higher priority on the same side. Z is also your cis. Higher priority across the double bond, 1535.5. That is your E, which is your trans. So that's about EZ or cis and trans. So EZ or cis-trans isomerism, they mean the same thing, just that two people doing the same thing from different perspectives. One is using higher priority or higher molecular mass across and the same side. But that one is saying the same group on the same side. That is on your cis and trans is talking about the same group on the same side. While trans is talking about the same group on across the double bond. So you have your cis and trans. While EZ is saying higher priority across is trans, then higher priority on the same side is your cis. Okay. So moving on, we'll be summarizing today's class. Let's summarize so that we can start. Then this one is already explained. Boot one in. Okay, let's look at this place here. We are saying this one, cis boot two in and Z. Why? We have higher priority on the same side. So this is how to write it. Z in bracket, then boot two in. Cis boot two in. Actually, there should be hyphen there. Cis boot two in, then Z in bracket boot two in. Trans boot two in or E boot two in, just like that. This one is not it's not cis on trans because we have higher priority on the same side. So it is not, it just a structural isomer, 2-methyl boot one in propane structural isomer. This one, boot one in also structural isomer. They are structural isomers. And in fact, they actually, we can call them what now? Position isomer. Is it position now? Position. No, chain isomer. Because on carbon 2, so it's on carbon 2. Okay, so that's about that for this one. Then we can continue the next slide. Okay. Okay, so we're wrapping up with physical properties of alkane. Physical properties of alkane. We'll be looking at boiling point, melting point, and solubility. The same way that we did for alkane is also the same thing for alkane. the higher the molecular mass, the higher the melting point. Why? The alkanes are non-polar. Alkanes, they are non-polar. Even though there is some extent of polarity, there's an extent of polarity. What do I mean by extent of polarity? What I mean is that double bond CH3. You will see that the carbon atom there, this double bond here, will affect this single bond. So double bond turns to single bond. There is a repulsion there. Double bond will repel the single bond. So double bond, single bond, there is slight polarity there because of the difference in electron density. So alkanes are slightly polar, but we can say they are actually non-polar. So they have dipole to dipole interaction because of the double bond inducing, repelling the single bond. So there is this slight, so there is a dipole force of attraction. Okay, so again, C2H4, C3H6, C6H10. The reason why the melting point is increasing or the boiling point is increasing is because of the number of electrons increasing. As molecular mass is increasing, number of electrons is increasing, van der Waals force increases, as well as what? The dipole force of attraction, induced dipole force of attraction. Induced in the sense that the double bond will induce a partial charge on this carbon like this, partial positive and partial negative happens here. So we have induced dipole there. Okay, so as the molecular mass increases, number of electrons increases, and then so van der Waals force also increases. And when van der Waals force increases, more energy is required. So the melting point and the boiling point will increase. But they will ask you, so, and they know what they are looking for. So it has to do with electron because they are virtually non-polar. So you can look for, when it's non-polar, you look for electron. The more the electron, the more the induced dipole force of attraction, the higher the melting point, the higher the boiling point. That is one. Then they are talking about branching. When alkane and alkene have branches, the one that is more branched will have the lower boiling point or melting point. Let's look at an example. If you compare this guy, 1, 2, 3, 4. Butuin. You compare butuin to this one. This one. That is a 2-methylpropene. Which one will have a higher boiling point or melting point? Let's call this one 1 and 2. 2 will have a lower melting point because it's branched. Butuin does not have any branching. It will have a higher melting and boiling point. While 2-methylpropene will have a lower boiling point. Why? The branching decreases the contact point. So when you arrange 1,2-methyl propane you arrange them over each other, the branching will distort the contact point. So 2-methyl butene will have a lower surface area. The lower the surface of contact, the lower the melting point. While butene straight chain on branch, we have higher contact and more surface to contact. The more the surface, the stronger the van der Waals force and the higher the boiling and melting point. So how do we explain this one in an exam condition? For this one, which is your butene, is on branch, has more surface area or has higher surface area of contact. So the higher surface area of contact will produce more electrons and more van der Waals force. But with the one that is branch has lower surface area of contact, so lesser van der Waals force, the lower boiling point. So the answer has to do with surface area of contact. So straight chain has higher surface area of contact, which will produce higher van der Waals force. While branch alkane have lower surface area of contact, lower van der Waals force, and then that will be lower melting point for that one. Okay. So let's continue. Okay. Okay, I didn't talk about so I need to talk about melting and boiling point. Solubility. They are non-polar. Since they are non-polar, they will not dissolve in polar solvent. They won't dissolve in polar solvent because polar will dissolve polar. So non-polar will not dissolve in polar. So, but they will dissolve in non-polar solvent like benzene, cyclohexane, and the rest. They are liquid, so they dissolve because they will form the same form of van der Waals forces. They can dissolve easily. That's solubility. But the first few ones like ethane, propane, they are gases. Why? They are gases, so you should know. But like pentane, they are liquid. Okay. Okay. Chemical properties. Chemical property. That's where we're going to stop. We can't finish it. Chemical property of alkene. The chemical property focus on the double bond or the pi bond. The pi bond is broken. You must note the following. Note the following, very essential. The pi bond or double bond is localized. The double bond in alkane, this double bond is localized. Localized. Once broken, cannot be reformed. Once broken, cannot be reformed. So it is weak. But the double bond in benzene, this double bond is delocalized. And I will explain the meaning of delocalized. It can move. It can move from here down to this place like this. Then this one can move down here, and this one can move down here like this. So it can rotate. So to form a new, so this one coming down, so it will be here, here, and here like this. Because double bond can move. So we call that one is delocalized. So double bond in benzene, delocalized. Once broken, it can be replaced. it can be replaced. So it is stronger, stronger or stable. It is more stable than the double bond in alkane. So double bond in alkane is localized. It can be delocalized. It can move. Why? Because you can have, so this alkane, so it can't go anywhere, it can't move. It can't move. But this one can move. The one in benzene can move. So it is localized. The once broken cannot be reformed, and therefore it is weak or less stable. The one in alkane, it is delocalized. It can be replaced once broken, so it is more stable. It is energetically more stable. For alkane, it is energetically less stable. That is the first one that you must know. So the double bond is the focal point of chemical reaction, the breaking of the double bond. So alkanes are nucleophile. Alkanes are nucleophile. So they will attack electrophile. Electrophile can be polar, like this one, can be polar, can also be non-polar. So the alkene has capacity to make non-polar molecule to become polar. Once you bring in a non-polar molecule near an alkane, it can make it to become polar. So I have an alkane in this wise, and if I bring in chlorine like this, the double bond will repel this single bond here and then drive this electron down, down, down. So the Cl will be partial positive here and partial negative here. So non-polar molecule like chlorine can react because once they come near double bond, they become polarized. So they have dipole. Explain why non-polar molecule can react with chlorine. We can react with alkane because they can react because once they come near the double bond, they are polarized. So they form partial positive and partial negative. So therefore, they can act as what? Electrophile. Now, you know the idea of the concept of electrophile. Let me ask you, what are electrophiles?
Electrophiles are species that are that lack in
Electron.
positive electron, sorry.
Okay, they are electron deficient species. They are electrophiles are electron deficient species. Um, Electrophiles are attracted to nucleophile because nucleophiles have excess electron. Nucleophiles are rich in electron. So we say nucleophiles are electron-rich species, but that is not the definition. Those are descriptive words. An electrophile is a species that can accept a pair of electrons to form a new covalent bond. An electrophile, the species capable of accepting a pair of electrons to form a covalent bond, while a nucleophile is a species with a lone pair of electrons that can be used to form a covalent bond. A lone pair of electrons used to form a covalent bond. So electrophiles are electron acceptor, nucleophiles are electron donor. So an electrophile is a species that can accept a lone pair of electron. That one we score. Okay. So electrophile are partial positive charge or full positive charge, or there is no any charge at all. Okay, that is about the foundation for the chemical reaction. Alkanes undergo electrophilic addition reaction. Electrophilic addition reaction. Rounding up, we
Did you say
this
alkane?
alkene,
Okay.
ENE, undergo electrophilic addition, and their reagent can include the following. I'll just list it and we'll continue next week. Include the following. Number one, can react with hydrogen. Number two, hydrogen halide. Hydrogen halide, which include your HF, your HI, your HBr, and HCl. Number three, steam. Number four, concentrated sulfuric acid. So we're going to consider two types of alkane. We'll be considering terminal alkane, and unsymmetrical alkane. Terminal alkane like CH2, double bond CH2. Just add your plus hydrogen, and there's reaction. Plus chlorine, just add it. So addition reaction. But when you have unsymmetrical alkane, like CH2, double bond CH, then CH3 like this, and you are adding HCl, where will the H go? Where will the Cl go? So we will talk about that one next week under the mechanism of reaction and other reaction. So, and finally, number 5, the reactions of alkane. Number 5, we'll be talking about oxidation of alkane. Oxidation of alkane. And then number 6 reaction that we'll talk about is polymerization of alkane. Polymerization of alkane. So we have how many now? Hydrogen halide, steam, concentrated sulfuric acid, oxidation of alkane, and then polymerization of alkane. So the reaction we'll talk about next week. Okay, so you may go ahead and read them, and then so that when we come to class, we can just be talking about it. While I round up, the time is on. I like organic chemistry very well. So I'm writing up with this one. If I have CH2, double bond CH2 plus hydrogen, there will be a reaction. There will only be a reaction where there is nickel catalyst to form CH2, CH2, CH3. So to form CH3, CH2, CH3. So you start with alkane, and you end with alkane. What will be the name of the reaction? That's the first thing you must know. What will be the name of the reaction?
Is it the
hydrogenation
yeah.
of alkane. What is the mechanism of the reaction? Electrophilic addition. This one can go with addition reaction. Addition reaction. Okay.
Okay.
Yes, electrophilic addition reaction. Mind you, alkane can also react with bromine, chlorine. Bromine is used to tell that one will get it. So hydrogen alkane or addition reaction, the philic addition reaction. The alkane will polarize the hydrogen. Why do I need nitrogen? Because of course, you know, H bond is strong, very strong to break. So it has high activation energy. So you need a catalyst to lower the activation energy. So nickel catalyst is needed. And sometimes you have about 150 to make it faster. Okay. To make the reaction very fast, you add heat to it, heat 150. So nickel catalyst is key to this reaction, nickel catalyst, to form that. Now, they will talk about the bond angle. Bond angle in alkane is 120. Bond angle in alkane is 109.5 degrees. So it has changed. So the bonding system has changed. So they can ask you different things. The bonding in alkane 120, alkane 109.5. Nothing more. Then the mechanism, they can ask you this mechanism, but it certainly is an addition reaction. Okay. So the remaining one will talk next week. You have any question?
No, sir.
So we have covered a lot today, especially the other one I explained for you, which is your structural isomerism. I didn't plan it at all that I was explaining, but I just find myself explaining it, and I'm sure you have gained a lot in that area. So when you take your past question, you will see questions on isomerism and so on and so forth. If I can see, I will send you a question on isomerism that you can look at how they are being asked. So next week is another day. Since there are no questions, I don't have any question to ask. So I wish you the best.
Hello?
I don't have any question to ask. So, but if you have any question, let me know. No question as well.
Oh, no, I don't. Not yet.
You have question? No.
I said not yet, not yet.
Okay. So when are you resuming?
On Monday.
Okay. So we are resuming at the same time as well. That's good.
Yes.
So enjoy yourself. My regards to your friend in school. And
Sir?
my regards to your friend in school.
Oh, okay.
And if anybody wants my service, please recommend the person. Thank you.
Okay, no problem.
All right. So enjoy yourself. Bye bye.
All right, thank you. Bye.